right, chapter 6, standard deviation. And the normal model. So to compare unlike data, we standardize data using z-scores. So this would be kind of something like, we wanted to see how you did in this class compared to forensics, let's say. Then this would be a way that we standardize everything because we grade differently. And you can see comparatively, like, say compared to the rest of the class, which like this class is, there's only 2 of you, so, you know, whatever. But like forensics, I know there's a lot. So it's like compared to the rest of your class, how did you do compared to, you know, Hope on the forensics test? Like, were you, you know, was she at the mean and were you above the mean, below the mean? Like, that's what this is going to help tell you. That's just like one like kind of quick example. So the formula for this is z equals y minus y bar over s. And these things each have a meaning. So y bar is the mean of the distribution. Okay, much like x bar that we've used before for mean. Y is the data value. And S is the standard deviation. So a z-score, which is what this is, tells us how many standard deviations a value is from the mean of the distribution. A positive z-value is above the mean. A negative z-value is below the mean. And the larger the value of the z-score, and it's really like the absolute value of it, because if you're -3 like away or you're +3 away, like that's in both cases still going to be considered unusual. So the farther the value of the z-score, or the larger the value of the z-score, the more unusual it is. And typically we say anything more than 2 z-scores away or 2 standard deviations away is what we would consider unusual. And you'll see why when we actually model out how much data falls in that region. So do a quick example here that goes with this. So the mean score on a test is 72. Okay, so that's going to be the mean score, so that's going to be your y bar. the standard deviation of scores is 4 points. So in the formula, that's going to be your S. Fenwick gets in, not on, gets an 82. Okay, so this number is going to be the data value. Okay, so it's going to be our Y. What is the Z-score for his test? So we would use the formula and we plug stuff in. So Z is equal to Y, which is 82, minus Y bar, which is 72, over S, which is 4, which is going to be 10 over 4, or 2.5. So we would say that Fenwick's score is 2.5 standard deviations above the mean. So good job, Fenwick. That means he did well on his test.
Is that easy?
Huh?
Is that easy?
Yeah. For now, but yes, it is that easy. No, not quite.
Because I had a lot of to realize this easy. Then I don't think it was for homework. It's nothing like this.
I mean, there's going to be more to it, but yes, just finding the Z-score is really that easy. And if it's like a lot of other stuff, like your calculator will give you this information as well, depending on what you're given. So, all right. So then a follow-up to this is that Fenwick's friend Chris says his test score has a Z value of minus 0.5. So what score did Chris get? So this case, we're doing the opposite. This is his Z value here, but we're still using the same mean and standard deviation. So now we're trying to find Y. So Y is what is unknown to us in this part. So I set it up the same way. So I have Z now is minus 0.5 equals Y minus 72 over 4. And then we just need to solve that. So multiply by 4, it's going to give you negative 2 equals Y minus 72. And then add the 70, so Y equals 70. So then from that, what? Yeah. So from that, we can conclude that Chris scored a 70 on his test. And that makes sense because we said that Fenwick was 2.5 above and he scored an 82. So for Chris to be below by the minus 0.5, then that means his score had to be less than Fenwick's. So our answer makes sense. So this probably is obvious, but whose test is more remarkable? Yep. Fenwick, because his Z-score is farther from 0 than Chris's. Obviously, Fenwick scored higher, so I would hope that to anybody that would be considered more remarkable, but if we were just looking at z-scores, that would also be the case. So when you shift data, the center moves, but the spread stays the same. Rescaling data changes the center and spread. So many pages of notes. All right. Next thing, a normal model is a way to make assumptions about our distribution based on the shape of the distribution a normal model, normal distribution is unimodal and symmetric. Okay, we would say roughly. It could be a little bit off, so it's not going to be like perfect, but so basically, I'm going to do my best to draw this, but essentially, it's not exactly even, but it's close enough. And also, another name for this is a bell curve, so if you ever hear that, that's what they're talking about. It is named based on its mean and standard deviation. Because it is a model, we use mu, so it's like it's the fancy U, Greek letter, for mean, and a sigma, I don't really know, it kind of looks like a sideways 6, for standard deviation. And these two numbers are the parameters of the model.
Why is that M so face?
It's a U, actually. It's the Greek letter mu. It's a fancy U.
You said you, but my brain didn't process it.
Are you
I feel like
flabbergasted
it's like an
again? I asked him that earlier. He said something and I was like, are you flabbergasted? And he's like, I am flabbergasted.
It's so funny. Because I thought it was an M for me.
Yeah, it's the Greek letter mu.
Here we are.
Just a fancy, basically cursive U.
Make a little note here.
Fancy U, not M. All right, so if you have N and then a parentheses, mu and sigma, okay, this is how we indicate the normal model that we are using. No. I mean, yes, that's how it's set up.
No.
Well, yes, that's how it's set up, but no, this isn't like to graph it. I mean, well, I guess technically speaking, I don't know. Graphing, yes, but not, it's how you do this. Like, the middle of this is the mu. And then every standard deviation you go away from it is a sigma. So this is how we indicate the normal model that we are using. The Z calculation for a normal model looks like, and this is going to look familiar, but Z equals Y minus mu over sigma. Okay, so mu is just another way to write X or Y bar, and sigma is another way to write the S. Eventually you'll find out that one is for population and one is for sample, but that's a little bit farther down the road. But your calculator can also give you both of those values from, I can't remember if it's one variable stats or if it's a different function off the top of my head, but anyways, your calculator can give you that information as well. And then just something to note that this is exactly the same way we calculate for any distribution. So anytime we're dealing with that stuff, that's how we calculate it. The standard normal model is written as N and then parentheses 0, 1. So the mean is 0, standard deviation of 1. And that's just to help us standardize so that we know exactly what we're looking at. It just makes it a little bit easier when we're doing stuff if it's like all been like looks the same, and it doesn't change the data, it just changes what it looks like. So we use this model when we have standardized R values to z-values. All right, this next thing is very important. You must verify that your data meets the nearly normal conditions before you use normal models. Check these conditions by making a histogram and verifying that it is unimodal and symmetric. Be sure to note that you checked the conditions. Okay, so usually when I do it, I'll do something like conditions, and then I'll just put a check mark with it to show that I checked it.
So it has to be, isn't it?
I mean, relatively speaking, it might be a little bit off, but and it's one of those things where it sounds bad, but like your book isn't going to necessarily give you something that's not. So it kind of gets to the point where you're just like, yep, conditions check. Because it really doesn't, they really don't do any that aren't. But if you were given something that wasn't unimodal and symmetric, then you should say you can't use a normal model because of that.
That's a lot of words for a math class.
Well, I do one more thing and then stop for the day because it'll be like a break, like one more little like topic thing. All right. Some orange. All right, the empirical rule. This is also known as the 68, 95, 99.7 rule. Those numbers are important. But we will have used them so much by the time that you get to a test or a quiz, you will have them ingrained in your brain. Considering we're about to write them like 3 more times just in this little section of notes. So,
Oh, I had numbers. So, oh, I know this room.
in a standard normal model, %68 of the data falls within plus or minus 1 standard deviation of the mean. 95% within plus or minus 2 standard deviations. And 99.7% within 3 standard deviations, or plus or minus 3 standard deviations of the mean.
Oh yeah, we did this in I think I want to say chemistry.
I think the empirical rule in chemistry means something else.
Hmm?
I think there's an empirical
Yeah,
rule in
there's
chemistry,
an-
but it means something different.
Yeah, there's an empirical rule in chemistry. I don't
Yeah,
remember.
'cause I remember.
I remember.
This was last year.
I'll have to ask Miss Marshall.
What's the empirical rule in chemistry? In chemistry, a chemical compound is the simplest positive integer ratio of an atom's present in a compound.
Sounds about right.
Yeah, 'cause I remember that in chemistry.
A little while ago for me.
I couldn't tell you what it means, but
All right, so drawing a normal curve then with this information.
it like looks the same as the other one.
Yes, but we're going to fill this one in. So the middle is going to be 0, and then you're going to go 1, 2, 3, -1, -2, -3.
I remember this from somewhere. I just can't.
I'm trying to think of what you would have seen this in
It
possibly.
wasn't chemistry.
I might briefly mention it in pre-cal at some point when we do something, but
Was it? It wasn't.
I'm trying to think of
Like,
where
we
you would
learned-
see
We
this.
learned this in the class. Like, they was teaching us how like teachers grade on the curve.
Yeah.
So this how they taught us.
Must be a teacher that did curved a lot then.
It had to be. my
No
mom-
one here curves.
It had to be my biology teacher because she curved a lot. I remember one time I got.
You took AP Bio?
Yeah.
That's pretty common, I think, because my AP Bio teacher curved everything. So she would, like, figure out what the average grade was, and then she would take the average grade and see how many points it took to get them to, like, the grade that she felt like people should be getting. So I think the grade was, like, an 85. And however many points the mean was away from the 85 is how many points she would add to everybody's test. But I'm telling you, like, I got, like, 47s on every test
Yeah.
without the curve.
Well, it is also AP, so it makes sense.
She would literally go online and like print off the AP test and give them to us, like for our actual testing class.
That's terrible.
And it's like all 5 answers look identical. It's like, sure, that one looks good.
Yeah, so I think because I had got like a 40 something on the test, and I looked in student view. That's what we use instead of grade. I looked on student view. It said I got a 79. And I was like,
And you're like, there's no way.
yeah.
I'm just drawing these lines to make it look a little easier. Normally, I don't draw them, but it makes it a little bit easier to see what we're dealing with the first time if you have them. So. All right, so this rule says that between plus or minus 1 standard deviation, we have 68% of the data. So 68% lies in here. Two standard deviations away is 95%. And then 3 standard deviations away is the 99.7%. Oops. Definitely didn't didn't draw that far enough. All the way over. There we go. Like something didn't look right. There we go. So that's to say if you're looking at your data and it is normal, then 68% of your data should be within plus or minus 1 standard deviation away from the mean. Plus or minus 2 is 95%. That's why we really say anything over 2 standard deviations away is considered unusual because it's only 5% of your total data that's outside of that range. So, we're going to go ahead and stop there. I'll do a little example of like what this would actually look like if you were given a problem when we start up on Monday, and then we still have 2.5 pages of notes left. Well, of these, but I've already gone through like 4.5 pages, so there's not actually that much left, but I mean it is, but it's not.